In this video, we are going to learn the Bernoulli rule. Bernoulli rule is applied when there's an indeterminate form. So there are four different type of indeterminate forms. In this one, we can talk about the type 1. Type 1 means you get functions that behave as 0 over 0 or infinity over infinity at the limit. So that's the goal of this video. Sometimes the Bernoulli rule also called the L'Hopital's rule, which is a historical mistake as this result was introduced by Bernoulli in 1694 and then it was published in L'Hopital's book in 1696. So let's try to learn what we mean by the Bernoulli rule. So let's try this as a theorem. Bernoulli rule. Suppose so we have like two functions. So if the limit of when x goes to a fx over gx either going to be 0 over 0 or infinity over infinity. So it's going to approach one of those cases, either 0 over 0 or infinity over infinity. Then what will happen? Then this limit actually can be found using derivatives. So that's the idea. So this same limit fx over gx, this is going to be equals to the limit when x goes to a f prime x over g prime x. So this is not the quotient rule. This is just you take the derivative separately and divide them and take the limit. So this is equal to that if the limit, this is very important, if the limit on the right hand side exists, and then also this a can be a finite number or infinite number. So so it can be finite or infinite. So this is the L'Hopital's rule. This is sometimes we call L'Hopital's rule, or this is the most appropriately this should be the Bernoulli rule. So let's try to look at several examples. So I'm going to highlight this one because this is the condition that you need to remember. And don't get confused with the quotient rule. This is not the quotient rule. You take separate derivatives and then divide them. So let's try to look at a few examples and try to understand how we can apply this. As the first example, we have limit x goes to 1, x cubed minus 2x plus 1 divided by x cubed minus 1. So if you get a problem like that, what we normally do is, we know that when x goes to 1, you can see that it is going to be 1 minus 2 plus 1, that means 0. And also bottom, when you plug in 1, you can see it is 0 again. So that means it's a 0. By the factor theorem, x minus 1 should be a factor. So what we do is we're going to find the x minus 1 factor from the numerator and the denominator and cancel out, and then you get a quotient, and then you can plug in the value if it is not something divided by 0 or 0 or 0. So that's like a normal approach. But what we do in this case, and you can see that when you plug in the value, you actually see that you get 0 over 0. So what the Bernoulli theorem says that instead of the functions, look at the derivatives. So we can look at the derivatives. So so we take the derivative as x goes to 1. So derivative at the top is 3 x squared minus 2 divided by 3x squared. That's what you get. Now we're going to see what will happen again. Like when you see x goes to 1, see that we get 0 over 0 again. We don't get 0 over 0 again. So that means we can simply plug in the value using the direct substitution property. So when you plug in the value, you can see that it's going to be 3 minus 2 divided by 3. When you simplify, it is 1/3. So that is the limit of this one. And you can also try the other method and using factors and see whether you get the same answer. You should get. So let's look at the next one. We have limit x goes to 0, square root 1 plus x minus 1 minus x divided by 2 whole thing divided by x squared. So again, as before, you can check the numerator and denominator, and you can see denominator is 0 already. Numerator is you're going to get 1 and then minus 1. So you get a 0 0. So since you get 0 0, So we can write it here 0 over 0 just to make sure you check the condition. And then what we do, we take the derivative. So let's take the derivative. So it's a limit. We still write the limit. X goes to 0. It should be the original limit. So let's take the derivative. Square root means half power. So if you take the derivative, you get 1 half 1 plus x to the negative 1 half times 1. So, by the chain rule, minus negative 1 derivative means 0, and then x half, so you get 1 half as the derivative divided by 2x. That's what you get. Now what you do, you try to see whether you can plug in the value or the direct substitution, and you can see when you try to plug in the value, what will happen in the numerator? Numerator again becomes 0, and denominator also becomes 0. So that means this is again a 0 over 0 problem. So we say it's a 0 over 0 problem again. So that means we can apply the Bernoulli rule again. So it is limit x goes to 0. So let's try to take the derivative again. If you take the derivative again, you can see that it is going to be negative 1/4 now, because you get one more 1 half, and then times 1 plus x to the, we subtract 1, negative 3 halves divided by 2. Now you're going to plug in the value, and you can see that when you plug in the value, everything works perfect. So you can see you're going to get, when you plug in the value, the numerator is going to be negative 1 over 4 divided by 2. So that means if you multiply the top and bottom by 4, you're going to get negative 1 over 8. So that is the limit for this problem. So let's look at the next one. As the next one, we have limit x goes to 0 sine 7x over sine 3x. So if you look at the graph of sine function, and you know that at the 0, so it's going to be 0. So when it goes to 0, and you can see it is 0. So that means in this problem you can see you're going to get 0 over 0 for the numerator and the denominator. So what we're going to do, using the Bernoulli rule, we're going to instead look at the derivative. So let's take the derivative using the chain rule. So you can take the derivative. So sine becomes cosine as 7x, and multiply by the derivative of the inside function, which is 7. And again do the same thing for the bottom. It is cosine 3x times 3. So if you are not familiar with the chain rule, and you can look at the video in the description, and there are like about 10 different problems in another video, and you can study that. Okay, so let's continue. And then what will happen is, so you can pull 3, 7 out. So you're going to get limit x goes to 0 cosine 7x divided by cosine 3x. And now look at the cosine graph. So you know, if you look at the cosine graph, what will happen at 0, cosine 0 is 1. So this is a cosine graph, but at 0 it is 1. So this is a cosine graph, this is a sine graph. So because it is 1, so you can see the numerator goes to 1 and the denominator also goes to 1. So that means your answer is going to be 7/3. So this is how you use the Bernoulli rule to find the limit of something like that. So this same technique you can apply for sine, tangent. So it can be tangent, or it can be sine and tan mixed. So it all works. Okay, so let's look at the next one. As the next one, let's look at a one-sided limit. The same rule applies to one-sided limits as well. So we have limit x goes to pi over 2 plus cosine x over 1 minus sine x. Normally, like these kind of problems we solve using a multiply by conjugate method. But let's see how we can use the Bernoulli rule for this problem. So, and then you can see, if you look at the graph of those two functions, so we know the graph of those two functions, sine and the cosine. So sine go through 0 and go like that, and then you can see it is pi over 2. So at pi over 2, the sine function goes to 1. And if you look at the cosine function, cosine start at 1 and then go down and go like that. So you can see the cosine function at pi over 2 becomes 0. So this is a cosine function. So these functions are good ones to remember because we can use this a lot. Okay, so it's pi over 2. So that means you can see that in this problem, the numerator is going to be 0 and the denominator is also going to be 0 because it's 1 minus 1. So it is also so this one is 0 and you can see the bottom is going to be 1, so it is 0. Okay, so that means we can use the rule now for this one. So we write 0 0, so that means limit when x goes to pi over 2 plus from the right side, so we take the derivative, so it is negative sine x. That's the derivative of cosine, and the derivative of sine means cosine with the negative sign is equal to negative cosine. So negative negative get cancelled out. So we only have limit x goes to pi over 2 plus. So we have sine over cosine. So what is sine over cosine? You know that sine over cosine means tangent. So you can write it like that, or you can actually make an argument what will happen at the top and the bottom. So now you can look at the graph of the tangent function, and we know the graph of the tangent function, they have asymptotes. So so there are two asymptotes. So the graph of the tangent function, and then so what will happen is going like that, go through 0, and on the other side it's going to go like that. I only exaggerate the value at pi over 2, so that's what we are interested in. So this is a tan function. It's a tan function. So what happened now is, and you can see when it reach pi over 2 from the positive side, you can see function goes to negative infinity. So that means this one is going to be negative infinity. So that's the answer you get for this problem. So let's look at the next one. So let's look at some infinity over infinity problems now. As the next one, we have a very interesting one. So let's say limit x goes to infinity, 3 minus 2x squared divided by 4x squared plus x plus 5. So like when you have a problem like that, what we normally do is we're going to divide the top and bottom by the largest power of the denominators. In this case, we can divide the top and bottom by x squared. So we divide by x squared and then see what will happen. But let's try to use a different approach. So we try to use the Bernoulli rule for this problem. And as you can see, when x goes to infinity, and you can see that the top and bottom goes to infinity. I just mean by infinity means it can be positive or negative infinity. So those are both infinities. So infinity over infinity. So that means we can look at the derivative instead. So let's do that. So limit x goes to infinity. So from the numerator, you're going to get 4x, and from the bottom, you're going to get 8x plus 1. So now we check the limit again. So you can see when x goes to infinity, you again get infinity over infinity. It's like a negative infinity or positive infinity, but we can just say infinity over infinity. So that means we can use the rule again. So what we do, we take the derivative again. So once you take the derivative again, you're going to get negative 4 divided by 8. So which is a number, that means the answer is negative 1/2. And you can see that using the other technique also you get the same answer. And also there's a shortcut. What we normally do is you look at the only the terms with the largest power. These are what we normally call the dominating terms. So we only look at the dominating term when x goes to infinity or positive or negative infinity, and then you just divide these two, and you can see when you divide those two, x squared get cancelled, you get negative 1/2. So that's a shortcut, and you can prove this using the Bernoulli rule. You get the same answer, but this is like more powerful because you can do many other problems than this. Okay, so let's look at the next problem. So as the next example, we have limit when x goes to infinity, ln x over x, and you can see that if you look at the graph of ln x, so this is again something you need to remember. So this is a graph of ln x. It's going to pass through 1, and this goes to negative infinity when x goes to 0 from positive. So you can see in this case actually you again get when x goes to infinity, ln x goes to infinity, x goes to infinity as well. So that means a 0 infinity over infinity situation. So we can take the derivatives. So we take the derivative when x goes to infinity, derivative of ln x. This is something we remember. So we know the derivative of the natural log function is 1 of x. So derivative of natural log function is 1 of x. So that means the top becomes just 1 of x, the bottom is 1. So if you want, you can rewrite this one like that, and you can see when x goes to infinity, numerator gets larger and larger, so that means it's going to be 0. So the answer is 0. So let's try to look at several similar cases that can be useful in the future. How about this one? If you replace x with the exponential function. So we have limit when x goes to infinity ln x over ex, and we know the graph of ex. So the graph of ex has this form. So that means it's going to grow indefinitely, this graph of ex. So in this case also you can see that you're going to get infinity over infinity. So that means you can look at the derivatives instead. So it's a limit x goes to infinity, and we know the derivative of ln x is 1 over x, and the derivative of ex is ex. So that what we can do is we can multiply the top and bottom by x, and then when you do that, when you multiply the top and bottom by x, you can write it like this: limit when x goes to infinity 1 over x ex. And you can see that all the terms are in the denominator, and if x goes to infinity, so that means in this case it's simply going to be 0. So it's very interesting. So that means when you compare ln x and ex, this means since it is 0, that means ex grow much faster than the ln x function. That's what it means, because the limit goes to 0. That means ex grow much faster. So let's look at one more problem. Using a similar approach, actually you can prove that. So I'm going to leave this as an exercise. You can prove that the limit when x goes to infinity ln x over any polynomial. So you have a polynomial here. For any polynomial, this is also going to be 0. So think about whether you can prove that. Just assume a polynomial and see what happens. So this is also a result. So these results are very important. So you can use them in the future. So I'm going to write this as a result. So for any polynomial, this one is 0. Okay, actually the more important result is this one, the one we had previously. So limit when x goes to infinity ln x over ex is equal to 0. So these two results are very important for future. So that means ln x grow much slower compared to those two functions. That's what it means. Okay, so let's look at one more last problem. So how about this one? So we have when limit x goes to infinity, 3 to the x minus 1 divided by 2 to the x minus 1. And then you can clearly see that when x goes to infinity, these the 2x or the power functions behave like exponential. These are exponential functions, so they behave like ex. That means pass through 1. Both of the functions, 3x and 2x, both have the same format. And then because of that, you can see that this is an infinity over infinity situation. So we're gonna look at the derivatives. So let's recall how to find the derivative of an exponential function, the power function. So the result is d by dx. B to the x is simply b to the x. You repeat that and times ln b. So we multiply by the natural log of the base. So that's the result we use here. So that means because of that, the numerator going to be 3x ln 3, the bottom going to be 2x ln 2. Now what we can do is we can pull out those ln 3 and ln 2, and then we have limit x goes to infinity 3x over 2x. Actually what we can do is we are not going to use the Bernoulli again. But what we can do, we can combine them. So when you combine them, you can see you can write this one as ln 3 over ln 2. You can write this one as limit when x goes to infinity 3 over x, 3 over 2x. But we know that 3 over 2 is greater than 1. Since it's greater than 1, this is like again like a power function, the exponential function. So, and then also since 3 over 2 is greater than 1, this is going to grow to infinity. So this is going to be infinity. So that means finally, the final answer is infinity times a number, so it's infinity. So the final answer is infinity for this problem. Okay, so this is how we use the Bernoulli type 1. So in the next video, we're going to talk about Bernoulli type 2. So thank you for watching.